Hi, in the last video, I discussed about how do we compare two population means when the sigma 1 and sigma 2, meaning if the population standard deviations are given. Okay, so in this video, I'm going to show you how to compare two population means by using the hypothesis testing when the population standard deviation sigma 1 and sigma 2 are not given. Okay, so all the steps of the hypothesis testing are the same. Only the difference here is, for example, step number 1 will be writing H0 and H1. Okay, so in this case, since we are comparing the two means, so the null hypothesis is mu1 minus mu2 equals to 0, and then the alternative hypothesis will be one of those mu1 minus mu2 greater than 0 for the right tail test, less than 0 for the left tail test, and not equals to 0 for the mu1 minus mu2. So there will be or not equals 0 for the two-tailed test. And number 2 is the test value, right? Test value. For the test value, the formula is t equals to, so as in the one sample test, we will use the t test here, x1 bar minus x2 bar minus mu1 minus mu2, which will be 0 if you are testing the equality, divide by under the root s1 square over n1 plus s2 square over n2. That's what you do. Okay, so this is the formula to find out the test value. Again, so this is the case of comparing the two population mean when the population standard deviation are not known but assumed to be assumed not equal. Okay, so they are the different sigma 1 and sigma 2. That's the assumption here. And so the method again, so to find out the number 3 is to find out the critical value, or to find out the p-value, we will need the degrees of freedom. Okay, so for the degrees of freedom, what is the formula? The formula for the degrees of freedom is minimum of n1 minus 1 and n2 minus 1. So minimum of the sample size minus 1. Okay, because there will be two sample size. For population 1, you will have one sample size, and for population 2, you will have another sample size. The sample size may be equal or not equal. It doesn't matter. So what we do is we will pick the smaller of the sample size and then do n minus 1. Okay, the sample size of the smaller sample and then minus 1. That will be the degrees of freedom. Okay, so that's the formula for degrees of freedom. So this degrees of freedom formula with this test statistic we call Burns-Fisher test. Okay, Burns-Fisher method. But the software calculator and the statistical software use another formula to compute the degrees of freedom. df equals to a plus b whole square divided by a square over n minus 1 plus b square over n2 minus 1. This is n1 minus 1, where a is s1 square over n1 and b is s2 square over n2. s1 square is the variance of the first sample and s2 square is the variance of the second sample. Okay, the choice of the formula does not affect the conclusion of the test in almost all cases. The method with these degrees of freedom is called the Wales test. So the software or the R will use this, basically this test. Okay, all right. So what are the assumptions here? Is the number 1 assumption is the sample size. The samples must be random sample. Number 2, the sample data are independent of one another, and the population variance are not given and assumed to they are not equal. And when the sample size are less than 30, each population must be normally or approximately normally distributed. So which is basically the assumption in the other problems too, right? I mean other cases too. Okay, so let us do one example here. So it says that a researcher wishes to see if the average weight of the newborn male infants are different from the average weight of the newborn female infants. Okay, she selects a random sample of 10 male infants. Okay, so let me list what are the given things first. Okay, so the given things are n1 is equals to 10 and then n2 is equals to what is n2? N2 is 10 male, and find that this, and the standard deviation is this. She select random sample of 8 female, so n2 equals to 8. What is x1 bar? Is the average of the male, so that is 7 pound 11 ounce. Okay, 7 pound and then 11 ounce. And then what is that for the female? So that will be basically, or so you know what, it is better to write the 7 pound 11 ounce as in terms of the ounce only, so which will be 123 ounce. Okay, for n2, for the second sample, the sample average is x2 bar equals to 116 ounce. Okay, and also what else is given? And the standard deviation of the sample is 5. So what is the standard deviation of the first sample? Is 8 ounce, right? So S equals to 8. See, the sample standard deviation is given, population standard deviation is not given, and here S1 is 8, S2 is 5, and what is alpha? Alpha is 0.05. Okay, is this left tail, right tail, or two tail? See, so it says that if the average weights of the newborn male infants are different from the average weight of the newborn female infant, it looks like it is two tail. So okay, let's read the last sentence. Can it be concluded at alpha equals 0.05 that the mean weight of the male is different from, again, so it is different from, meaning it is two-tailed. Okay, so two-tailed. All right, so this will be not equals to 0, right? And then you just plug in the value of x1 bar minus x2 bar, so this will be 0 because we have mu1 minus mu2 equals to 0, and plug in the value of s1 square over n1, s2 square over n2. So basically I have calculated that will be 2.268. that's what you will get in number 2. Okay, in number 3 again you can use the p-value method or the critical value method. Okay, for the p-value method, since this is the two-tailed test, what we do, and this lies on the right side, right? So this is two-tailed test and the test value lies on the right side here. So this is the test value here. So that is, we denote by t. So we need to find out the 2 times the area right of that. Okay, so the p will be 2 times area right of t. Right of t. What is t? T is that 2.268. That will be 2 times. To find out the area right, we need to do p norm, right? But here we need to do 1 minus p norm, and then 2.268. what is the degrees of freedom? What is the smaller sample size? Is 8, so that will be 8 minus 1, right? So that is 7. You do this way, right? 2 times that, just the p norm will give you the area left of that, but you need to find out the area right of that. That's why you need to do 1 minus p norm. Okay, so if you do this, you will get, basically you will get 0.0576. That's what you get. And if you want to do the critical value method, so that is alternative method. Okay, so critical value method. So when you do the online homework, you can do the p-value method only. So value method. So what is alpha? Alpha is 0.05 two-tail, right? Two-tail, meaning that you need to find out alpha half here. So alpha half will be 0.025, and then if you draw that, and then you will get, so that alpha half will go to the two ends, right? So 0.025 here, 0.025, and we denote this by negative t alpha half, and then another alpha half goes here, 0.025, and this is positive t alpha half. So how to find out negative t alpha half? Negative t alpha half will be will be q norm, because we are finding the t value, right? Q norm 0.025, and then what is the degrees of freedom again? The smaller of those, so that is 7. If you do that, you will get negative 2.365. That will be negative 2.365. This is that value, and this value will be positive 2.365. Okay, so this will be positive 1. So let's write down plus minus that. It will be plus minus that. You can write that way. Okay, now how do I decide? Is this p value bigger than alpha? Number 4. Since p is bigger than alpha, we do not reject, right? We do not reject h sub 0. But how do we decide here? Is this test value falls in this shaded region, or do not fall this in this shaded region? Because see, this value is negative 2.365. This value is positive 2.365. So definitely this value will fall in the unshaded region, meaning non-rejection region. Okay, so we do not reject the null hypothesis. Look at this. Using the critical value method, since the test statistic, so for the p-value method, if since p is greater than alpha, we do not reject h sub 0. And in the critical value method, since the test statistic does not fall in the critical or the shaded region, we do not reject the null hypothesis. So summary is, there is not enough evidence to support the claim that the mean of the weight of the male and female are different from the mean of the weight of the female. So mean of the weight, the average birth weight of the male infant is not equals to average birth weight of the female. So we reject that claim, meaning that we actually indirectly support the null hypothesis. Okay guys, so this is how you do by hand. But when the data set is given, we use R directly. How do we use R? Is, see, let us look at this example. The number of grams of carbohydrates contained in 1 ounce serving of randomly selected chocolate and non-chocolate candy is listed here. Is there sufficient evidence to conclude that the difference in the means is statistically significant? Use alpha equals to 0.10. That's the question. So what we do for this is we just copy this data set as a chocolate. See, chocolate equals to C, and then copy that data set. Remember that you need comma there. And if there is more than one data, then we need C and then parenthesis. Okay. And for the non-chocolate, you copy that. See, they have the different sample size. Okay. So how do I test this? Is you just do t.test and chocolate comma non-chocolate. It does not matter. The order does not matter. You can write non-chocolate first or chocolate second. It does not matter. Mu equals to 0. This is very important thing. What is that mu equals 0 means? Mu equals 0 means that mu1 minus mu2. This part. That mu1 minus mu2 here is mu. Okay. And paired is false because this is the not paired one, right? Because this is two different samples here. And variance equal is also false because we were saying that variance are not known and then not equal as well. And alternative is two-sided and confidence interval is 0.95. Okay guys, so all these paired, variance equal, and then all these things, so their order can be different. You can write the alternative first and then other way. So you can do that way. It's not a problem. Okay guys, so basically you run this code. Let me show you how I did here. Look at this. Look at this one. Let me see if I can show all of these. So see, example from slide 17. This is slide number 17. And then null hypothesis, null is mu1 minus mu2 equals 0. Alternative is not equal 0. Two-tailed test. So let us run this chocolate, non-chocolate, and then t-test. Look at this. So the t-test gives you the p-value is 0.1131. Okay. So p-value is 0.1131 means we do not reject the null hypothesis in this problem too. Let us see what I said. Since p is greater than alpha, we do not reject h sub 0. That is null hypothesis. Hence there are, so it should be hence there are not enough evidence that the carbohydrates content in the chocolate and non-chocolate candies are significantly different. So there are not enough evidence to conclude that. Okay guys, so this is how we do by calculating. It's just right away, I mean by using R. So it is just right away. So you just copy the two codes and then do to data, and then you do t.test and do all these things. Okay. Oh, by the way, I think I made a slight mistake here because the question is saying alpha is 0.10, but I took alpha confidence level is 95. It should be 0.90, right? It should be 0.90. If you run that, what do you get? You will get still the p-value is still 0.1131. The p-value does not change here, but the confidence interval will be changed there. Okay. So see here, this code should be 0.90. I'm sorry about that. So this must be 0.90. Okay guys, let me change this. Look at this. So since alpha is 0.10, so 1 minus alpha must be 90%, right? So it should be 0.9. So confidence level is 1 minus alpha, which should be 0.90. Sorry about the confusion there. So let us do, see this is the formula to find out the confidence interval. It is similar to the previous one, just the difference is there is S1 square, S2 square, and there is instead of G there is T. Okay. So and again the degrees of freedom will be, to find out T alpha half, you will need degrees of freedom, will be the minimum of N1 minus 1 and then N2 minus 1 as above. Okay. And note again, if 1 minus alpha confidence interval for the difference between two means contains 0, then we do not reject the null hypothesis, implying the two means are equal. So this is the same concept. Okay guys. So what I want to do here is I want to do another example here to construct a 90% confidence interval, but I want to do this in R. Okay guys. So let us do this problem in R. How do I do this problem in R? So actually you will do the same thing as you do by hand, but since you do in R, so you don't need to do the calculation. R does the calculation there. Okay, so what are the given things? Let's first list the given things, and then we will do that. So this is from, I think it is from slide number 19. Okay, so this is from slide number 19. So slide 19, what are given? N is given. So N1 is 40, right? N2 is 40, also 40. X1 bar is 172.5, and then X2 bar is equals to 60.6, right? And what is S? Sample standard deviation 119.5, and then S here is 138.1. Okay, so this is what is given. So let me write down what is the question is talking about. So cotinine is produced in a body when nicotine is absorbed, thus a good indicator of nicotine. Okay, the following is the summary of the data from a study of cotinine level measurement in smokers and non-smoker sample. Construct a 90% confidence interval. So it is saying 90%. So 1 minus alpha is 90%, that is 0.9. So alpha will be 0.1, right? And then what do you do that? So alpha is 0.1, and so what will be alpha half? Alpha half will be 0.05. Okay, interval. It says construct a 90% confidence interval for the difference between the mean cotinine level of the smokers and non-smokers. Can you claim that the smokers have different means? So this is two-tailed test. So what I'm going to do here is I'm going to construct a confidence interval. Okay, two-sided, or the two-sided confidence interval, and then if that confidence interval includes 0, then we do not reject. If it does not include 0, we will reject. Okay guys, so these are the given things that we tried. Okay, so how do I find out the T alpha half? Because the formula here, look at this formula. The formula here is needing T alpha half, right? Negative T alpha half and positive T alpha half. What is happening here is, so this is like, this is the left 0.05 and this is the right 0.05, right? 0.05. This is negative T alpha half. Why do we denote by T alpha half? Because sigma 1 and sigma 2 are not known. That's why we denote by, we use T test and we denote by T alpha half. So how do I find out negative T alpha half then? Negative T alpha half will be Q, it should be QT. Okay, so QT and then 0.05 degrees of freedom will be, so both of them are 40, right? So it will be 39. The smaller one will be 39. So you can do that way and then find out the critical value there. Okay, so here I used exactly the same formula that I mentioned that before. So x1 bar minus x2 bar minus T alpha half, that value, right? See, x1 bar minus x2 bar, that is inside the parenthesis, and then plus QT. Why did I do plus although there is a minus? Because the negative T alpha half is given by, this is that negative T alpha half. Okay, this is that negative T alpha half. This is given by QT, positive QT. So I wrote positive QT 0.05 and then 39 degrees of freedom times square root of that and then comma that values. Okay, so same value, but here you see that QT. To find out that positive one, what do? What is the total area left? Because QT needs the area left of that value. If you want to find out this value, you need the total area left of that. So this is 0.9, 90%, right? And this is 0.5, so 95. So what I did here is QT 0.95 comma 39 times that under the root S1 square over N1, S2 square over N2. So let me run from the beginning. What do I get? If I run from the beginning, this is what I get, 63 through 160. Okay, so you see that the value of the confidence interval, the bounds of the confidence interval is between 63.24 through 160.55. So what does it that means? This means that since 0 is not included, since the confidence interval does not include 0, we reject H sub 0. Okay, let me copy this and then say that. So what I want to do here is I want to write the parenthesis and then do that thing. Okay, this is what I got in the answer. Okay, so since the confidence interval does not include 0, we reject the null hypothesis. Hence there are enough evidence to support the claim that the smokers have more average cotinine level than non-smokers. Okay guys, so this is how you you test the hypothesis for the equality of two means by using the confidence interval. Okay, there is a note here. If only one of the population standard deviation is known, for example, if sigma 1 is known but sigma 2 is not known, in this case we use two sample t-test. We still use the t-test, not the z-test. Z-test is used only if the sigma 1 and sigma 2 are given, meaning the population standard deviation of the both samples are given. Okay, but if one is given and other is not given, then we use this same formula for the degrees of freedom. The R will use the same degrees of degrees of freedom formula, and we use exactly the same technique. Only S1 square will be denoted by replaced by sigma 1 square. Okay, all right, and follow the same step. Recommended strategy is if you have two independent sample data and comparing two means, the recommended strategy is two sample t-test with unknown and unequal variance. This is the best method if you are comparing two samples with unknown variances. Okay guys, all right, so the next test we are going to talk is testing the difference between two means independent samples. The samples are not related to each other. Sigma 1 and sigma 2, meaning the population standard deviation unknown, but they are assumed to be equal. The previous one was they were assumed not equal, not known and assumed not equal, but here we are assuming they are equal. So in which situation we consider that the variance of the populations of the two samples are equal is this. See, sometimes we take two random samples from the same population with known variance. That means if you are taking two samples from the same population, then the variance of those population will be equal, because the population for the both sample will be the same population, right? So they have the same variance. That's what it means. In that case, the population of the both samples, I think it should be unknown variance, you guess. Okay, the population of the both samples are same, and you may assume the equal population variance. Okay, for two independent samples, if the population variance, population standard deviations are not known but assumed equal, we again use the t distribution and the sample standard deviation. While using t distribution, we use the degrees of freedom is n1 plus n2 minus 2. Don't forget this. This is a different formula for the degrees of freedom than we had in the previous case. Okay, where n1 and n2 are the sample sizes. For the test statistics, this is the formula for the test statistic. x1 bar minus x2 bar minus mu1 minus mu2. This is the value from the null hypothesis. Instead of s1 square, s2 square, or sigma 1 square, sigma 2 square, here we use sp square. That is called the pool standard deviation is sp. So sp square will be pool variance. Okay, this is the pool variance, and this is also the pool variance. All right, where the pool variance sp square defined as the average of the variance of the samples weighted by degrees of freedom is calculated. This is the formula to find out the pool variance. Okay guys, so we find out the pool variance and we use there to find out the test statistic. All right, so all the steps to do by hand are exactly the same. Now how do we do the confidence interval? Exactly the same method. So x1 bar minus x2 bar, t alpha half is same as before, but instead of s1 square and s2 square, what you do is you do the pool variance. So sp square over n1 plus sp square over n2, and this is the same thing here, where the degrees of freedom is n1 plus n2 minus 2. Let us do one example by hand. Okay, so the horned lizard, this is the scientific name for that. The horned lizard is a species of lizard that has fringes of spikes surrounding their head. Herpetologists are interested to test whether the size of the spikes protect the lizard from being predated from one of its main predator, long-horned shrike. This is the scientific name. The researcher identified the remains of 30 horned lizards that had been killed by shrikes and measured the length of their horns. As a comparison group, they measured the same trait of 154 horned lizards that were still alive and well. The summary is given below. These are the statistics. Okay, x bar for the leaving one, the sample bar, sample average is how much? It is 24.28 for the leaving one. Similarly, for the non-living, for the dead one, it is 21.99, a little bit smaller, right? Similarly, standard deviation is S equals to 2.63, here 2.71. So sample size for the living is 154 and sample size for the dead is 30. So the idea here is, with alpha equals 0.05, can we conclude that the surviving lizards have longer mean horns than the one that were in? So we want to test that. Okay, guys. So you see that in both of these samples, living and the dead lizard, so on both of these samples, okay, the population of these both samples are the same, right? Because see, these two samples were taken from the same population. One of them are living and one of the sample were dead, right? But they were taken from the same population. So we can think of like, okay, so the population variance of, or the population standard deviation of these both samples will be equal. So you can think of that way. Okay, guys. All right, that's what we are assuming in this case. But later, after the variance test, I will show you how to check whether the variance of those two samples are equal or not. We will discuss that later. But for now, we are assuming that the variance of the population of both samples are equal, because it is the same population for those both samples. Okay, guys. So how do I do this? Again, the same thing. So if you do H0 H1, right? So H0, number 1 is H0, mu1 minus mu2 equals to 0, meaning that the living and the dead have the same average horn size, right? And H1 is, because we have do they have the same or the longer? Okay, can we conclude that the surviving lizard have longer mean horns? So what we do is mu1 minus mu2 is greater than 0. That's what we do for the for the alternative hypothesis. Number 2, we use exactly the same idea here, the t. So the test value will be t equals to x1 bar minus x2 bar, okay, minus, that will be 0, right? Because mu1 minus mu2 is the from the null hypothesis. And you find out the pool standard deviation and find out pool variance square over n1 plus pool variance square of the sample over n2, where what is sp square is n1 minus 1 times s1 square plus n2 minus 1 times s2 square over n1 plus n2 minus 2. That's what you do, and find out sp square. Okay, and number 3, for the p value, we use the t distribution. Okay, guys. So I have done all these things in the so in the R. This is what we got here. So n1 is 154. Okay, did you see that? n1 is 154 here. n1 is 154, right? n1 is 154, n2 is 30, n2 is 30, x1 bar is 24.28, x2 bar is 21.99, s1 is 2.63, and then s2 is 2.71, alpha is 0.05. Okay, so the null hypothesis is equals to 0. This is how I want you guys to do the homework if I ask this type of problem. Okay, and then h1 is mu1 minus mu2 greater than 0, which is a right tail test. So what is this pool standard deviation? Okay, so pool standard deviation is this, and we will use sp square there. So sp is square root of that. So why did I do sp instead of sp squared? So I cannot write sp squared here. I can do sp squared, like I can name that way, but I cannot name like sp and then square. Sp, I cannot name like this. I cannot name like this. It will show error. Okay, so what I can do though is I can do sp and then square, like type in text and then use that sp squared instead of sp. Okay, so square root of n1 minus 1 times s1 square plus n2 minus 1 times s2 square, and whole divided by n1 plus n2 minus 2 and the square root. So let me run all these, and then I found the t. That's the test value. Okay, let me run from the beginning, line 109. So that's what we have given, and then sp is found to be 2.64. that is the pool standard deviation. Okay, and what is the test value? Test value is 4.34. okay, and to find out the p value, we need the degrees of freedom. Degrees of freedom is n1 plus n2 minus 2. So now, since this t value, the test value is positive, so to find out the p value, what do we do? We find the p value is area right of the test value, right? Why? Because it is positive. So area right of t. So how do I find the area right of t? 1 minus pt, right? So actually you don't need the parenthesis here. So you can delete that parenthesis, 1 minus, and then pt is that value, and then division. Why do I do 1 minus pt? Because pt will give you the left area of t. We need to find out the right area of t for the p value. And when I do that, I got a very small number. You see that? P is 0.00001, which is less than 0.05. Since p is less than alpha, we reject H0, meaning hence we reject H0 means we will support this one, right? So hence there are enough evidence to conclude that surviving lizards have longer mean horns than that were eaten. So what the scientists can conclude here is, okay, so the lizard use their spike on their head as their protection, right, from their predator. So you can conclude like that. Okay, guys. All right, that's what we do for the confidence interval and the hypothesis testing of two means when two variants are not given, two independent samples. Okay, two variants are not given and assumed are equal. Okay, guys. Thank you.